as with boundary layers, turbulent flows require a little bit different method than laminar flows. So we're going to start talking about turbulent flows. In round pipes, the transition to turbulent flow begins at a Reynolds number of about 2,300. Then we have what we call transitional flow. And then this transitional region lasts up to about Reynolds number of 10,000. So fully turbulent flows have Reynolds numbers greater than 10,000. This is a general guideline. It's applicable to a wide range of conditions, but the actual value could be higher or lower depending on the design of your system and some other specific situations. So laminar flow only exists at very small velocities or in very small pipe sizes. At higher Reynolds number, small variations known as roughness elements on the channel wall cause perturbations or small fluctuations in the flow. What this does is enhances the mixing between the fluid layers, so momentum can be transferred more easily between those layers. And this tends to reduce the average velocity gradients, much like it does in a laminar boundary layer versus a turbulent boundary layer. When the Reynolds number is high, viscous forces are no longer strong enough to damp out these fluctuations. And this results in chaotic motion, according to the scientific definition, like chaos theory. It's not random, it's just too complex for us to predict. And the reality is most practical flows that we're going to encounter will be turbulent. We start by analyzing turbulent flows using the Navier-Stokes equation. Now, the next step is to break up the variables. We're going to use velocity as an example. We have an average part, which is the V bar, and we have a time-dependent part, or a variation part, a fluctuating part, which is V prime. And then after we do some averaging, we come up with this equation where we have a bunch of average things, but we have a new term here. It's very similar to the Navier-Stokes equation, but we have an additional Reynolds stress. Now, the Reynolds stress, which is circled here, is not actually a stress, but what it does is represents the effect of fluid mixing, or advection, on the Navier-Stokes equation. It behaves like a stress in the equation, hence the name. This is the Reynolds average Navier-Stokes, or RANS equations, used in many CFD codes. Now we have a major challenge. How can we model the Reynolds stress in order to predict turbulent flows? One of the first models for turbulence was the mixing length model developed by Ludwig Prandtl of the boundary layer theory. And he applied boundary layer theory to this idea of turbulent flow in some geometry. So he divided the flow into the boundary layer, where the flow is laminar, and we can directly solve the Navier-Stokes equation, and the turbulent core, where the flow is totally turbulent, and we can ignore the viscous forces. These two simplifications allow us to more easily solve the behavior. And for the turbulent core, the result was Prandtl's universal velocity profile. Now, Prandtl's universal velocity profile is something basically what it sounds like. From experimental data, it was found that kappa in this equation was 0.4, and then the value of the constant was 5.0 for the turbulent core. And it was found that that holds for any fluid, so hence the universal part of the name. Now, this model is very accurate near the wall. However, it has some shortcomings. We need to know the wall shear in order to calculate this, because we need the wall shear in this equation. It's also not very accurate near the channel center. You can see the results match very well with experimental data, except for in this transition region, where you have a region in between the two important regions where the laminar flow assumption is not quite right and the turbulent flow assumption is not quite right. So we have a transition. It's also not very accurate near the channel center. At the channel center, we have a symmetry condition, which means the gradient has to be 0. But the mixing length model doesn't allow us to predict that. So there are some uncertainties in those two regions. Now, we sometimes use the 1/7 law, or 1/7 power law, as an approximation to the velocity profile. It's sometimes useful, but it's not very accurate near the wall, and it still doesn't give us very accurate results for wall shear and pressure drop. However, it can be important for understanding the flow. Normally, we know the average flow rate, and we need to find the wall shear. This model gives us the velocity profile if we know the wall shear. So how can we translate this and make it something that's a little bit more useful? We can do that with what we call the Darcy-Weisbach equation. It's how we predict head loss. From Poiseuille's equation, we know that we can relate head loss to the friction factor. Now, for turbulent flow, we don't have a theoretical model for the friction factor like we did from Poiseuille's equation. So we rely on experiment. We collect a lot of data, and then we perform curve fits. And what we end up with are equations like this. Now, the Colebrook equation is the most widely used. However, you'll notice that it's implicit. There's a square root of f on both sides, and there's not really any way to solve this to get f on one side. So that requires an iterative solution if you know the Reynolds number and you know the roughness of the surface. You could also use the Holland equation. The Holland equation is actually just an approximation to the Colebrook equation. The benefit is it does not require iteration. However, it's not quite as accurate. It's generally within 1% or so of the Colebrook equation. For smooth pipes, the Blasius equation is often used, but it requires that the roughness of the pipe be 0. It's got a very simple form, though, so it might be a reasonable first approximation prior to a more detailed analysis. You'll note that the Colebrook and Holland equation have the roughness of the surface, so we need to know what that parameter is. It's very important for turbulent flows. Now, different surfaces are going to have different roughnesses. The roughness basically has dimensions of length, and it characterizes the average size of the imperfections on the surface. So make sure you pick the right material and use the right roughness when you're solving problems. Now, the Moody diagram is a graphical representation of the Colebrook equation. It's very useful for some basic hand calculations. For Reynolds numbers less than about 2,300, you can either use 64 over Reynolds number, or you can just look it up on the Moody chart. For Reynolds numbers between 2,300 and about 4,000 or 5,000, you have this transitional regime, and it's very uncertain. So the gray region on the Moody chart reflects that uncertainty. And then the last thing I want to mention is the fully rough zone on the right side of that dashed line. So in this case, the friction factor is not really a function of Reynolds number anymore, but it is a strong function of relative roughness. Now what happens is the Reynolds number increases, the thickness of the boundary layer decreases from Prandtl's mixing length model. And eventually, the roughness elements on the surface actually are larger than the boundary layer thickness. And what happens is you have a strong form drag on those roughness elements rather than viscous drag. And if you remember, going back to our discussion of drag on spheres and cylinders, form drag is almost independent of Reynolds number. So at very large Reynolds number, almost all of the roughness elements are larger than the boundary layer. And we have almost all of the flow resistance due to pressure or form drag on these roughness elements. So oftentimes, if you don't know the Reynolds number of a flow, but you expect it to be large, you can start your problem by assuming that the flow is in the fully rough zone as a first guess. And then maybe you have to iterate a couple of times to find the actual flow friction factor. Now, the correlations we showed here can also be used for things that aren't circular, like square or rectangular or elliptical ducts. The problem is they can't be too exaggerated. For a rectangular or an elliptical duct, you should have an aspect ratio no larger than 3 or 4, which means the long side is no more than 3 or 4 times the size of the short side. So the hydraulic diameter, which is what we use in these cases, in the Reynolds number and other quantities, is 4 times the area divided by the perimeter. Now, for a circular duct, the hydraulic diameter is equal to the diameter. But basically, it represents the diameter of a circular pipe that has the same volume to surface area ratio as the flow channel you're looking at. Now, if you have an exaggerated flow channel, we can't use this, it won't be accurate. So, as always, use experimentally determined values if you need exact, precise information.